So in the previous lecture, we came up with the equation for AF of t using the first order approximation, and today we'll be discussing what exactly is h dash of t. It is not very difficult to realize that h prime of t, or the perturbation Hamiltonian, or the time dependent perturbation, should come from light. So which means that we need to look at light, and that's the content we're going to learn today in this video. Now light can propagate, and let us assume that it is propagating in the x direction, and then you have an electric field that goes up and down in the y-axis and the magnetic field in the z-axis. The propagation direction, magnetic field and the electric field are all perpendicular to each other. Now for propagation direction, there is always a vector called r, which is nothing but the radial vector. That means you are going away from some point. And epsilon is for electric field vector, and for magnetic field vector it is b. These are unit vectors which are along that direction, and you will see that the electric field vector always keep changing direction. Not only electric field vector but also magnetic field, it keeps on changing the direction, but then the propagation direction is always along the x direction. It only follows one direction, and that it is not going to change its sign. The other important thing is something called the wave vector. Now wave vector is nothing but how many units of wavelength does the wave travel. Now this is given by k is equal to 2 pi by lambda. So this is wave vector. Now we'll be discussing the four Maxwell's equations. So they are del dot E is equal to 0, del cross E is equal to minus dou B by dou T, del dot B is equal to 0, del cross B is equal to minus mu 0 epsilon 0 dou E by dou T. These are the general description of light in terms of Maxwell's equation. So now that you can see, Maxwell's equations are associated with electric field as well as magnetic field. So electric field has three components: Ex, Ey, Ez. Same goes for the magnetic field. It's Bx, By, Bz. So totally there is 6 variables, but 4 equations. So for 4 equations there are 6 variables. So there is somewhat redundancy in the number of variables. But that's not the point I really wanted to capture. The most important point that I would want to say is that we treat Hamiltonian in terms of kinetic energy and potential energy, but here in the classical light they mention about the electric field and magnetic field, but what we want is kinetic energy and potential energy. So in order to convert these electric field and magnetic field into appropriate potentials is what we need to do. So now we have to make a transformation. So this transformation, we would start describing the electric field, the magnetic field in 2 different components, which are called the vector potential and scalar potentials. So it's nothing but we have to convert the electric field to potentials. In order to do that, we do a transformation. You understood why? So because Maxwell describes about the electric field and magnetic field, but we are using Hamiltonian, and Hamiltonian only talks about the potential energy, kinetic energy, so we have to do all this stuff. Fine. So scalar potential is denoted as phi, and which is just a number, and vector potential is a. And it has a component ax, ay and az. So totally here we have 4 components, but earlier we had 6 components, right? So we can conclude that by moving from field to potential, we can reduce the number of variables from 6 to 4. And in electrodynamics, the way we can fix the number of variables is done by Coulomb gauge. So we use Coulomb gauge to change the number of variables, or to fix the number of variables, we can say. So Coulomb gauge is a constraint in which we say that phi is equal to 0 and del dot A is equal to 0. Okay. By the way, E is equal to minus del phi minus del A by del T, and B is equal to del cross A. And on applying the Coulomb gauge thing, we'll get E to be minus dou A by dou T, and B will be the same. There will be no change for B. It is always del cross A. Okay. By the way, E, let us say we had a vector, unit vector epsilon for E, and we have a unit vector B for small b for magnetic field. Okay. It turns out that A will also be along the unit vector of epsilon. A along unit vector epsilon, and because it is just a type derivative, so direction is not going to change, but del cross A, but in case of del cross A is perpendicular to B. And also we know that for E and B is perpendicular, right? And so the direction of the electric field and the vector potential will be same. It's like the zeroth law of thermodynamics. One is equal to the other is equal to, so A is in contact with B is in contact with C, therefore there's a relation between A and C. Similarly, as I said, when curl of A is going to change, A will be perpendicular to B, and we know that E is perpendicular to B, so there will be a relationship between E and A. So direction of the electric field and the vector potential will be the same. They are not going to be this direction is same, they are not going to be the same, because A, that is vector potential, is a time derivative of E. Then you have, okay, then we have wave vector K, which it tells you the propagation direction. So which means that totally what you have is that wave vector K vector is perpendicular to E vector, which is perpendicular to B vector. Okay, so K is perpendicular to both E and B. So this is a conclusion. Okay, so we can say that the additional propagation of the wave vector, the epsilon, that is the electric field vector, B, that is a magnetic field vector, all are perpendicular to each other. So that's the conclusion I wanted to draw. Now very generally, let us take vector A to be equal to A naught e raised to I k dot r minus omega t plus e raised to minus I k dot r minus omega t. Okay, here the dot product of this one, here the dot product k dot r is nothing but the dot product of wave vector and the propagation wave, which propagation direction, which simply means that the propagation wave and the wave vector are on the same direction. So which simply means that this term is called the phase factor. Okay, yeah, so we know that this term is nothing but 2 cos of k dot r minus omega t. We just have to substitute this one, so we get it as 2 a naught e0 cos k dot r minus omega t, where r is the propagation direction, k is the wave vector, and omega is the angular frequency. Now that we have A, using Coulomb gauge, we can find E to be equal to minus dou A by dou T, which is nothing but minus is there, then cos ka derivative is minus sign, so it becomes plus sign, and there's a 2. Okay, 2A epsilon 0 sine kr minus omega t, and there's a minus again, minus of omega, so it be multiplied by minus omega. Okay, so you get like this, and now I can substitute minus 2 a naught omega to be e naught, so I can rewrite it as E is equal to E naught epsilon naught sine kr minus omega t. So the vector potential is a function of cos theta, and the electric field is the function of sin theta, and both are in opposite directions. So we can say that A and E are out of phase with each other by pi by 2, and also we can say that if E goes up, A comes down, and vice versa. Similarly, if you take an example of a pendulum, the momentum and potential, they are out of sync with respect to each other. That is a case of the harmonic oscillator of a pendulum. So this is the same thing, similar to the electric field and vector potential. When one is maximum, the other is minimum. So I will stop at this stage and we'll continue in the next lecture.